This is lecture 18. In this we study the determinant trick and prove an important result that gets used all the time called Nakayama's lemma. Proposition. Let M be a finitely generated R module generated by a set M1 through Mn. Let phi from M2 itself be a R linear map such that I an R ideal. I is an ideal of R. Phi is an R linear map such that phi of M is inside I times M. Okay. So both these are submodules of M. So suppose that there is a containment. Then there exists A1 through AN such that AI is inside I to the I for all I, and there exists I1 to I such that this is equal to this, and phi n plus A1 phi n minus 1 plus phi A n minus 1 phi plus A n times the identity of on M is 0. Okay. So let's just make sure we understand what the statement means. Notice that phi is an element, is a homomorphism from M to itself, so we can compose it multiple times and we can talk about powers of phi. So phi n means phi M to M to M to M2, that composition n times. So this is n minus 1 times and so on, and this is just 0 times identity matrix. Okay. This is once and this is identity matrix. Okay. Now where does this expression live? Well, this is also because these are R linear maps, we can talk about A1 times, A1 is an element of the ring, so you can talk about A1 times a map, and we can talk about sums of such maps because maps form a module. So that's where this expression lives. Okay? So this is a statement about certain map being 0. Proof is very elementary linear algebra, except that we have never thought about these things for modules. That's it. Okay? We have done this many times for or variations of this for vector spaces. Okay. So proof. Okay. We know the hypothesis is that phi m is inside IM. Okay. So for 1 less than I less than n, write phi of mi, so that's inside here, as Aij Aj. Mj, and j goes from 1 through 1 to n. Okay. So let me just explain why this is possible. Phi mi is an element inside here, so we can take some ideal generator of the ideal times m1 plus something in I1 plus times m1 plus something in I1 times m2 and so on, and when we combine it we will get an expression like this. Okay. So the Aij will be inside I. So this is the observation that such a thing can be written for each I. So this can be expressed in terms of a matrix, which is that phi of mi, so let's write this in terms of a matrix. Okay. Phi of m1 is, so it's just a11 m1 and so on. So we can put a11, a12 and so on, a1n as the top row, okay, and so on. Phi of mn we can write, okay. So this is an1, an2, sorry, here ann, and what multiplies here is again m1 to mn. Okay. So this made this n by n matrix, and this is n by 1, and here is n by 1. Okay. So we get this, and this is exactly where the finiteness is used, that we get a matrix expression like this. Okay. Then, so here is the trick that we have done for vector spaces, but not, or when we study eigenvalues, etc., we have done this. But so now we are thinking about these elements as not just elements of R, but elements of the R of a larger ring, which also includes the endomorphism phi. Okay. So in that ring, which is a commutative ring because every element of R commutes with phi, that's the linearity, R linearity of phi, and then multiples of phi commute with each other because it's just the same, same map. Okay, so if you have a single map, this is a commutative ring, and so in this ring what we have is that phi minus a11, a21 and so on, an1, and then a12 phi minus, oh sorry, these should be minus, we are subtracting the right side from the left side, a222 and so on. So I should say not in the ring, over, this is 0. So m is also a module over that, and in that, over that we get this expression. So this expression, this matrix has entries in this ring and not in R. Okay. But what does that say? That says, so now we do Cayley-Hamilton theorem, or yeah, Cayley-Hamilton theorem. So in linear algebra, we use it to find the inverse of sorry, not Cayley-Hamilton, Cramer's rule, I'm sorry. They're Cramer's rule. They're saying, but Cramer's rule. Okay, we use it to find the inverse of a invertible square matrix by taking the adjoint and dividing by the determinant. But if you don't do that, the statement is the following. If you don't try to divide by the determinant, the statement is the following. So first of all, let's call this matrix A. Maybe. Okay, so call this matrix A. Okay. So now Cramer's rule, it says adjoint of A, the way it's usually defined in a linear algebra over fields course, times A is determinant of A times identity. Okay, this is true. The only problem in trying to find inverse using this is if determinant of A is not invertible, we won't be able to divide it. But this statement is true over any commutative ring. This is the n by n. Okay, so this is what we have. Okay, so now let's multiply both sides by adjoint of A. So now this one says, so if you multiply both sides by adjoint of A, we get that determinant of A times this vector m1 through mn equals 0. But what does determinant of A look like? Okay. This is where the expression looks exactly like the way we would construct the characteristic polynomial. It is just a polynomial in the in phi, where the entries will come the way we compute determinant, and okay, so the determinant of A has a form phi to the n plus some a1 phi to the n minus 1 up to an minus 1 phi plus some an identity matrix on M, identity map on M. Okay, so this is form. So this is an element of R adjoint phi. It's not an element of R. Okay, but what does it say? It says determinant of A times mi is 0 for all I. In other words, determinant of A times m is 0. Okay. In other words, this is a 0 map. Remember, this is an element of this. This is thought of as some powers of phi, which are endomorphisms, and R linear combinations, that is an endomorphism. So this implies that determinant of A is the 0 map. Okay. I mean, a function is 0 is the 0 map. So this is okay. So this is the proof of the and then by one can check that the coefficients have this property, that they are increasingly larger powers of phi. That's a property of the determinants. Okay. So this is the proof of the theorem of this determinant trick. Okay. So now there are many applications of this. Okay. So corollary. M finite, so variations of, corollaries always will apply for finitely generated modules. If M is finitely, let M be a finitely generated module. Okay. If Im is equal to M, then there exists some x in R such that x kills M and x is congruent to 1 modulo I. Okay. In other words, in the ring R mod I, x is same as 1. That's what x is congruent to. Okay. So x minus 1 is inside I. So proof. So we need to understand this condition M equals phi M in terms of the determinant trick. So this result, this proposition is called determinant trick. Okay. So we need to understand M equals Im in this context. Well, the map that we'll have to consider is identity. So phi equals identity. So then we are saying M is inside Im. But M is inside Im means M is equal to Im. Okay. So we need to understand this. So apply proposition with phi equals identity map on M. This is a proof, I'm sorry. Okay. So apply the proposition with this. So now what do we get? So then phi to the, so notice that if you take identity map and raise it to any ith power, this is just the identity map itself. Okay. So we get a1 through an inside I such that 1 plus a1 plus a2 plus an times identity. So that phi to the n will all factor out as identity of map on M equals 0. Okay. So now let's define, so notice that this element is inside, so call this element B. and B is inside I. Okay. So now what do we know? 1 plus B times M is 0, right? Because 1 plus B times identity M is just, I mean, it doesn't change M at all. So if you take this composite, I mean this whole map and apply it to an element of M, it is just this element multiplying that element of M. Okay, so this is just 1 plus B times M is 0. And let's define X to be 1 plus B. Okay, so that therefore we get xm is equal to 0 and x minus 1 is inside I. Okay, so this is what we are asserting. Another important corollary. Okay, so yeah, so this is sometimes called Nakayama. So any version of this is called Nakayama's lemma, but maybe only the local version we will say Nakayama's lemma. So this is. Okay, and we will usually write NAK to abbreviate this in these lectures. Okay, so what does that? What does the statement say? Suppose that Rm is a local ring, M finitely generated. If M is equal to MM, the maximal ideal times the module itself. So this is a submodule of M. If M equals this submodule, then M is 0. Okay. So proof. Apply previous corollary. Previous corollary to get X in R such that X kills M and 1 minus X is in the maximal ideal. Okay, but let's see what X is. Okay, so we claim that X is a unit. Okay, so consider the ideal generated by X. Okay, if X is not a unit, then there exists a maximal ideal. I mean, then there's only one maximal ideal. Then M contains the ideal X, and this implies that 1 is inside M. Every proper ideal is contained in a maximal ideal. If X is not a unit, then X is not invertible, then this is a proper ideal, and it must be inside the maximal ideal, therefore the unique maximal ideal, and therefore from this expression we get 1 is inside M. This is a contradiction. Hence X is invertible. Okay. Let Y be its inverse. When we say invertible for multiplication, and here we mean its multiplicative inverse. Okay, so then Y times X times M, which is same as 1 times M. On this side it is 0, so this is M. Okay. So it is this version that we often use as Nakayama's lemma in many applications. So if you have a local ring, a finitely generated module, if M is equal to MM, then M is 0. Okay. just one more corollary. So this is another application of the same result. It's just a variation of Nakayama's lemma, or we can call this the Nakayama's lemma then. Okay. So let again M be finitely generated over local ring Rm. Okay. Let x1 through xn inside M be such that I'm sorry, this is okay, such that they generate, sorry, this is correct, they generate their images such that their images in M mod mm generate M mod mm as a R mod m module. This is a vector space. This is a R mod m is a field. Therefore, M mod mm is a finitely generated module over it. So it's a finite dimensional vector space. So then we can talk about some elements. And elements of here are residue classes of elements of M. So let's just pick n elements in M whose residue classes will generate this finite dimensional vector space. Then x1 through xn generates M as an R module. Okay. So this is how, so let me just read this once more. Let M be a finitely generated module over R mod Rm, local Rm. And we have a finite generating, so we take some finitely many elements inside M whose images in the quotient generate the quotient module over R mod M. So this is a field. So this, and since M is finitely generated, the quotient is also finitely generated over the quotient ring. So this is a finite dimensional vector space. And we're just saying pick a spanning set, but pick elements in M whose images form a spanning set. Then those elements generate M as an R module. Okay. So proof. Let N be the submodule R linear combination, R multiples and sums of these n elements. So this is a submodule of M. Okay. What do we know about this module? Okay. So let Y be inside M. Then, so we'll put a bar to denote. So we will put bar to denote residue classes mod mm. Okay. So now what do we get? So we get that Y bar, so there exist, so we get, there exist some elements in R mod M, but so maybe I should just say M, some elements in R mod M, so we could just take elements in R itself, and okay, there exist R1 through Rn in R such that, so Y is in M, so if you look at its Y bar, image in M mod mm, this is Ri bar, Xi bar. This is the hypothesis that M mod mm is generated by these elements, n elements. Okay, but what does this mean? So this means that Y minus the sum is inside M times M. Okay, so every element can be written as a sum, as an element of n plus an element here. So this implies that M is equal to n plus mm. So this is what we have. So where does Nakayama Lemma come to picture? Okay, so now let's consider M mod n. Yeah, let's consider M mod n is finitely generated Rm module over Rm. Okay, and if you multiply this by M, if you write M mod n mod M times M mod n, this is the same as M mod MM plus n, okay, isomorphic to, this is 0. M is equal to this was the hypothesis, so this is 0. Therefore, by Nakayama's lemma, M is equal to n. This is what we wanted to prove, that those elements X generate M. Okay, so this is what we want. M is equal to this submodule, which is what we wanted to prove. Okay. So this is the end of this lecture, and in the next lecture we will discuss a little bit about spectrum and some topology on spectrum called Zariski topology, and so the what we want to understand, I mean, how we will proceed that is to understand the what is behind primary prove the results about primary decomposition and associated primes, and how it fits in, what is, I mean, why is it relevant in this when we study solving equations V of I, looking at 0 sets of ideals, etc. Okay, so this is